that there are many higher order ripples present whatever we convert from AC to DC. Like, for example, if you see this waveform, this kind of waveform will get repeating, and by help of this switching function expressions, where we try to visualize all the ripple factor, and the pure DC component was really a small, its magnitude was really a small compared to other ripples. Even from this waveform, you can visualize that, yeah, this waveform has so high ripple, del V naught, and your output average voltage is like kind of Vm by 2 pi or Vm by pi. So that I showed in my last lecture, and after that, we tried to we tried to find out the output voltage just with the help of this expressions of Fourier series of switches, and we calculated for half wave rectifier Vm by pi. And how did I move ahead? I just took V naught is equal to H1 into Vs, and we know the expression, or we know the, you know, or what are the periods, or what kind of waveform will constitute this kind of expression. So we knew already that H1 is this d plus summation of 2 by n pi sine n pi d cos n omega t. And here, if it is like diode kind of uncontrolled switch, then we can take d as half, and after I put d equal to half, and we now, um, after writing this expression of H1, if we multiplied it with Vm cos omega t, so cos omega t will lead to a DC and second order ripple if for the particular case of n is equal to 1. Okay, so, and the major chunk of this expression or this magnitude is dVs, and dVs, just by looking, it seems that it is average DC component, but it is not, because here the supply is Vs is equal to Vm cos omega t. So that much is for guaranteed ripple. That is your fundamental highest order ripple. That is first order component. So that was zero point 0.5 into Vm cos omega t. So its magnitude was Vm by 2. Means whatever the supply we are giving, the peak, this is known as Vm. This is peak. So whatever the supply we are giving, that itself is ripple when we multiply it with half. So that's why it was important. Okay. And then we moved ahead with full wave converter. And again, what we did V naught is equal to H1 Vs minus H3 Vs. Okay, so minus why? Because this node is connected to this. Let me highlight. So this node V node is connected to positive, and when H1 will conduct, H1 and H2 will conduct simultaneously, and when H1 and H2 will conduct, this node will be connected to this. So the polarity of both the switches are different. So hence, what we did, we considered H1 minus H3 into Vs. And after that, a very interesting property we found out. What are the benefits of full wave converter? Because we are investing something, right? We are investing in number of switches. So we want some improvement in performance. We want some outcome. So for that purpose, I showed that if you do H1 minus H3 Vs, your first, the dominant highest order component of ripple, dVs and dVs, that would get cancelled out, and the major part of your ripple will be eliminated. So these were the two conclusions. Dominant first order ripple is getting eliminated, and also your magnitude is getting twice of what we used to achieve in half wave converter. So here the magnitude was 2 Vm by pi, and in half wave rectifier it was Vm by pi. So that was the motivation. And yeah, so after that, we, like I told that in this session, I will derive the Fourier series of this IS, or whatever the Fourier series of IS will be, that we have to see now. And yeah, with the help of the same switching function approach. Okay. Yeah, so this was all about last lecture. If any doubt about last lecture, you can ask now or later also. No issue. Okay then. So moving ahead then. So here we plotted the waveform of IS. And first we know if I naught is constant and DC, which is kind of ideal scenario, but if you provide sufficiently large inductance, you can get such kind of a waveform with a very, minute ripple. So whenever H1 and H2 will conduct, IS is same as I naught. The direction of IS is same as I naught. And whenever H3 and H4 is conducting, the direction of IS is reversing from the supply side, if you see. And again, it will go like that, H3 and H4, that I told in last session also. So now we know that IS will be in terms of I naught. I want to write IS in terms of I naught, and in between, the switches will come, right? So IS will be, I think I can write like IS is equal to H1 into I naught minus H3 into I naught, right? Because again, the same reason here, polarity of current is changing, and IS is just getting, you know, getting pulsed with a switching function or switch of H. So whatever the nature of switch of H1, that would get associated with the nature of your supply. So hence I can write like H1 I naught minus H3 I naught. Okay. So again, we can do all those jugglery, and like H1 is equal to D plus summation n is equal to 1 to infinite 2 by n pi sin n pi d cos n omega t. And again, H3 will be shifted by 180 degree. Yeah. Someone had any doubt to ask? Okay. It will be again D is equal to 2 by n pi sin n pi d cos n omega t minus pi. So after that, uh, after we have written this expression, now we can simplify it.
Hello.
Yeah, hello.
Sir, can you tell me how the current equation has derived IS?
Okay, okay, sure, definitely. See here, how did we write voltage? V naught is equal to H1 into Vs, because Vs is reflecting to V naught node when this switch is closed, right? And this minus Vs is reflecting at this node when this switch is on. Now, in similar manner, I naught and Is. So Is will flow through H1 when H1 is on, right? So I can write when H1 is on, Is is equal to I naught. Okay. And when H1 is off, then this current will zero, like no current will flow through H1, and this Is will get reversed and it will flow through H3, and again Is will be same to I naught, but it when H3 will be on. So hence I can write H3 I naught. Is it clear?
Yes, sir.
Okay, thanks. So again, we can plug in all those values and we can get the expression of Is in terms of I naught. So d will get cancelled out and you can write like n is equal to 1 to infinity 2 I naught by n pi sine n pi d cos n omega t minus cos n omega t minus pi. And again, this cos n omega t and cos n omega t minus pi, if you take n is equal to 1, then it will be 2. But let us. So here d now we can take as half because H1 is conducting for half of the time period. So overall, you will get n is equal to 1 to infinity when d is equal to half. And yeah, so basically you can live till this point. This will be your Fourier series of source current. Okay. So from this expression, you can calculate any order or anything of. So if we need to compute distortion factor, right? Distortion factor will be based on your Fourier series, right? And that was the purpose to derive this Fourier series. Then we can know all the components of current, all the order of ripple currents or fundamental or whatever. So what is the expression of distortion factor? Can anyone tell me what is the expression of distortion factor? It is basically fundamental of source current and its RMS value we will take, or anything, even peak value if you will take, that should be also fine because it will be ratio, so by root 2 by root 2, just for sinusoidal, not for all cases. But generally it is a fundamental component of your source current divided by total source current of RMS, right? So IS1, I think we can calculate from this expression, and IS just from this expression of IS in terms of I naught we have seen. So this was the expression of IS. The magnitude is varying from I naught to minus I naught, and we can calculate the RMS of this kind of waveform. If you think in terms of RMS, it will be 1 by T Is square dt, and for a time period, right? So again, 1 by 2 pi 0 to pi I naught square into dt was I, or d omega t you can take because we are dealing in angles. So omega t. So here omega t was 2 pi and here omega t is pi, plus pi to 2 pi minus I naught square into, sorry, I should write now dt. In next step, it will be simplified, right? So if you compute, it will come as I naught. Okay. So IS1, ISRMS is I naught, and IS1 RMS, like fundamental RMS, will be for computation of fundamental, we need to put n is equal to 1 in this expression. So cos omega t and cos n means n is equal to 1. So cos omega t minus cos omega t minus pi, that will lead to 2 cos omega t as we solved in last session also. So and d is anyway half. So sine pi by 2 is 1. So IS1 RMS we can write as 4 I naught by pi, and that's it. Cos omega t is the, its variation, how it is varying, but magnitude of IS1 RMS divided by root 2, because this is the magnitude and sinusoidal fundamental. So for RMS of sinusoidal fundamental, we divide it by root 2. So you will get 2 root 2 by pi. And now if you put in the expression of distortion factor 2 root 2 by pi and I naught also, I naught divided by I naught. So it will be 2 root 2 by pi, and this is your distortion factor. And now total harmonic distortion, that is called as THD, total harmonic distortion. Its expression is 1 by distortion factor square minus 1. So if you put this, let me calculate, pi by 2 root 2 square minus 1. So it is 0.4830. So if generality rate is written in percentage, so percentage PhD we can write as 48.34%, and that is really high. So yeah. So your source current would be distorted by almost 50%, and that is not a good thing. And there are some ways to reduce this kind of distortion. Okay, so for that purpose, if I think some, yes, Saurabh, please.
Sir, how do we get that 4 by pi? I am not listening that clearly.
4 by pi, which one? This,
IS1.
okay, okay, IS1, okay. See, what I told, that if you just need to put n is equal to 1, because this is the Fourier series of IS. If you need to compute IS1, you just need to plug the value of n is equal to 1. So if you put n is equal to 1 here, n is equal to 1 here, and d is anyway half, and cos omega t minus cos omega t minus pi. Since cos omega t minus pi is minus cos omega t, so it will be 2 cos omega t, and 2 cos omega t will be multiplied with 2, so it will be 4, and pi is already there. So 4 by pi I naught cos omega t. IS1 is
Yes,
4.
sir.
You got it?
Yeah, yes, sir.
Okay, thanks. So that was about it. So Yeah, so there are some ways people would, controlled kind of rectifier. So, uh, what does they do? Till this point, I took the help of switching function, but from after this point, uh, I have to use all those conventional things, whatever has been used in textbooks and all. The reason behind is that, you know, it will get lengthier and lengthier as we move ahead. And for that thing, if you apply everywhere, then you will get more distorted kind of thing, and you will get more number of terms in your expression. So, and you do not want to do that in such a less time of where less time is, allotted to you to solve a particular question. So, I just try to explain those concepts with this, just to realize that how much ripples are present in this kind of converters, and how to compute, at least for in easy way, how to compute for single phase rectifiers. Okay. So if any doubt till this point in this topic, you are free to ask. And now we will move ahead with controlled rectifier. Okay, so I am assuming that everything is fine. Now we can go ahead with controlled rectifier. Okay. Yeah. So single phase controlled rectifier. So what do we mean by controlled rectifier? Anyone?
Instead of diodes, SCR are used, which we can control the pulse in which
Huh, that's right. So why do we want to control those things?
to reduce ripple.
That's one thing, to reduce ripple. Other thing, you might have studied in machines as well. VYF control, right? So,
Yes, sir.
yeah, increase efficiency. Yeah, you can say, because you will conduct the switches for, a lesser period of time. So you can reduce the switching losses or conduction losses. So that you can reduce the losses, and indirectly you will increase your efficiency. That's correct. Yeah, so I was talking about VYF control in machine. Since I am from machine background, so I want to discuss that point. Generally your uh, inverter, all those machines nowadays, all those drives are fed with, sorry, all those drives are fed with your inverter, if you are aware. So, like nowadays, all those motors or drives are fitted in all those electric vehicles, your scooters, four-wheelers. Those are fed with your three-step, your three-phase VSI inverter. And those inverters are again connected to either rectifier or DC to DC converter. Okay. So now, if you have DC converter in this all those drive systems, so and you want to feed your AC source, okay, and that will go through your DC source, because the let me draw those steps. So let us suppose this is the motor, okay, it is. it will take sinusoidal supply. Okay, we have battery. Battery which will have your DC link, and in between you will have an inverter. So here your DC will be converted to AC and your motor will start driving. But in case you want to regulate this DC link voltage, okay, and you somehow you replace the battery and you connect with your AC supply whenever you charge your battery. Okay, so whenever you charge your battery, your AC supply will be there. Either it will be your single phase charger that is considered as a standard charger, which takes like long hours, 6, 7 hours. Whenever you sleep at your home, your vehicle will be charged. And other thing is your DC fast charger. Whenever you stop in between of your travel, you can plug in for 15 to 30 minutes, and your vehicles will be sufficiently enough charged to go for another 100 miles or so. So, many times we need to control your voltage. In inverters, you can control with sine PWM modulation, where you modulate your switches in your inverter so that you get lesser magnitude. Okay. And in AC to DC converter, since you have V naught is equal to 2 Vm by pi, and I will derive this expression into cos alpha, and that alpha is nothing but your delay in your switching pulses, or how much delay you are providing for the triggering of the pulse of your thyristor. So that is your alpha, and if alpha you keep increasing, your magnitude will keep reducing, right? So the amount of or the desirable value of output voltage you want, that will be regulated by your alpha, and yeah, you will get, and maximum you can get 2 Vm by pi. So you can control your voltage less than the rated value, right? You can't increase it. To increasing your voltage, you have to again connect your DC to DC converter or something so that you get enhanced value of voltage at this side. So yeah, so that was one aspect. We want control of voltages and all. So that is a really a good thing about these rectifiers. Okay, so that was it. So now I will start drawing some waveforms. Okay, so now onwards, I will consider Vs is equal to Vm sine omega t. Why? Because everywhere it will be fed from sinusoidal source, and in almost all the questions of previous year gate, you will see only Vm sine omega t. Okay. So with this supply, V naught is Vs is equal to Vm sine omega t. What kind of output voltage you will see? So this is your Vs. Okay. Now you are giving your pulse with some delay, as I mentioned. So let us consider this as alpha, this period. Okay. This is anyway pi, 2 pi. Okay. This load I did not mention which kind of load. So that I will keep drawing and I will keep mentioning that which kind of load is there for this kind of waveform. Yeah. So now your output voltage will start following since you have provided some delay at alpha. Okay. So it will start conducting from alpha H1, H2, H3, H4. Okay. So whenever this part is positive, your Vs is positive, and let me provide the polarity also. So whenever your supply is in positive domain, your H1 and H2 will be in forward conducting mode, right? Or forward biased mode. And it will be in forward conducting mode when just you provide the gate pulse. So you provide your gate pulse at delay of alpha, then your H1 and H3 will start conducting and it will follow as it is the supply is. However, it is not looking like similar, but it is same. Just assume it is same. Okay. After that, pi. What will happen if in your load, let us suppose that you have only resistive load. Okay. If you have only resistive load, case one, R load. Okay. When you have only resistive load after pi, okay, again the trigger will be provided at this instant, pi plus alpha, right? But in between pi to pi plus alpha, okay, these switches will be in forward biased mode. H3 and H4 will be in forward bias mode from pi to pi plus alpha. H3 and H4 will be in forward biased mode. But they will start conducting after alpha, like from pi plus alpha. Okay. Why? Because your resistance does not contain any energy to freewheel the so that it can supply some energy back to the source again. Okay, so resistor is passive device. It only dissipates or it it does not store anything, right? Like inductor or capacitor, they store energy for finite amount of time, but the resistor does not contain that property. So for that reason, it will not conduct from pi to pi plus alpha. And as soon as we provide trigger at pi plus alpha, again, V naught will be equal to your Vs. But now, as I mentioned that H3 and H4, when they will conduct, your Vs polarity will oppose and it will be minus Vs. So again, V naught is equal to minus Vs for pi plus alpha to 2 pi. It's too bad. And this peak magnitude is your Vm. This was for R load. I hope for R load there might not be any doubt. For next thing is RL load, right? So for RL load, if again there would be two things, and let me derive the voltage. Okay, I will derive once in the end expression of voltages and all. First, we understand what kind of waveforms will be there. If you are comfortable in drawing the waveforms at any time with any kind of circuit, then calculating the expression of voltage would not be a big deal. Okay, so it was VR. Now for case 2 when load is RL, there would be two scenario. Okay. In one scenario, again, L would be sufficiently large that it will feed back the current to source or energy to source, and then the value of L would be quite large, and it will conduct from pi to pi plus alpha. Okay, it will conduct for this period. Let me draw this in second figure. Okay. Yeah. So it will feed back the energy from load to source if L is sufficiently large. Okay? And it will keep repeating again when at pi plus alpha H3 and H4 will be triggered. Okay? And it will free will through these same switches H1 and H2. So H1 and H2 will conduct for this period. Here also same H1 and H2 for this period, and H3 H4 for this period. So again, when H3 and H4 will start conducting, it will go till 2 pi plus alpha. Okay, so this instant is pi, pi plus alpha, 2 pi, 2 pi plus alpha. Okay, so for this period, and another case is when L is large. Another case is your L value is not that much large, so that it is living in between. Okay? It is living in between. Let us suppose that it will conduct till this point, and after that it will not conduct. So let me draw it for separately also. In between, let us assume this value is pi plus gamma or something. Okay, so this is gamma. Okay, so this is pi plus gamma, and this is pi plus alpha. Okay, so again at alpha, your H3 and H4 will start conducting, and it will follow like this. Okay? It will go on. So when L is small, okay. I hope it is clear till this point. Next,
Yes, sir.
yeah, thanks. So from now onwards, battery will come in picture as I was mentioning battery charging. So RE kind of load. So RE load is S3. RE load is known as battery charging, and case 4 will be RLE load. And which kind of load is it? Which part of drive it is associated with? It is considered as uh, motor drive kind of load. Okay. Now, as we have, drawn the waveform till RL load. So I would like to derive the expression till this point, so that we will be comfortable till this point, and after what we will go in RE and RLE kind of load. Okay. So for R load, okay, V naught average we need to find out, since we have derived the average value of voltage. Okay. Sorry, since we have drawn the waveform of your voltage, so you can easily integrate from alpha to pi. You will take time period of pi because it is repeated afterwards. Its time period you can consider for pi. You know why? Because it is getting repeated after pi period. So you do not need to integrate for entire 2 pi. You can do that, but it will be just waste of time. So from alpha to pi, it is following the supply, right? So Vm sine omega t d omega t. Okay. So now we can write it as Vm by pi sine omega t d omega t is minus cos omega t integration. So cos alpha minus cos pi, right? It will be Vm by pi 1 plus cos alpha. Am I doing? Yeah, yeah, it is fine. What we were getting in uncontrolled kind of rectifier, there the value was V naught is equal to 2 Vm by pi, okay? And you can kind of verify it at this stage of if you put alpha is equal to 0, you will get cos 0 1, and it will be again 2 Vm by pi. Then you can be satisfied that your calculation is correct. Okay. So this is for V naught average R load. Now here for RL load, same thing we can do because we have the waveform, right? We have this waveform in front of our eyes. We know that it is starting its conduction from alpha. Okay, so 1 by pi alpha 2, it is conducting till pi plus alpha, and Vm sine omega t d omega t, and it will be Vm by pi cos alpha minus cos pi plus alpha, and cos pi plus alpha is minus cos alpha, so it will be 2 Vm by pi cos alpha. Okay, so again, if you put alpha is equal to 0, you will get 2 Vm by pi. So side by side, you can verify the magnitude. So I think it is all about when L was large, when L is large, and this is known as continuous conduction mode because your load current is consistent throughout the time period, so it will be continuous conduction mode. For DCM, we not average we can write because we have again the waveform, right? I'm I can't emphasize much about waveform. If you have waveform in front of your eyes, you can derive anything from it. So this is kind of waveform here. So 1 by pi, it is conducting from alpha to pi plus gamma. Vm sin omega t d omega t. Again, you will get Vm by pi cos alpha minus cos pi plus gamma, and again we know pi cos pi plus some theta is minus cos theta, so Vm by pi cos alpha minus cos gamma. Oh, sorry, plus, because minus minus plus. So again, when gamma would have been alpha, then this expression would have been 2 Vm by pi cos alpha. Okay. And if gamma would have been 0, then again you can go back to the R load because your gamma is 0. It means, and alpha is also, sorry, and it is also in discontinuous conduction mode. After pi, it is not conducting. Then you will get Vm by pi 1 plus cos alpha. Okay. So is there any doubt in this calculation of average voltage of output?
No, sir.
Okay, fine. So now we can move ahead with RE load and RLE load. It will be just a bit different than others. Let me first flip it. A small overview of R load graph. Okay. Didn't I explain about R load?
Yes, sir. Small bit.
Okay, okay. So see, after pi in your converter, let me bring back the converter also. Hmm. So see, H1 and H2 will conduct till they are in forward bias mode. Okay. So, and we are giving pulse at alpha. H1 and H2 will conduct from alpha and they will remain in forward bias till this instant of pi. Okay. Now, after pi, till pi, you are satisfied, right? It is conducting till pi. After that, what will happen? Mm, this H1 and H2 will go in reverse biased mode, and H3 and H4 will again come in forward biased mode, but they will not in forward conducting mode. Why? Because they haven't been provided the pulse, okay, or trigger. So when they will be triggered at pi plus alpha, then again this load will start conducting. So this R load is also your in discontinuous conduction mode. Okay. Is
Yes,
it
sir.
fine, Saurabh? Yeah. Okay. So now, yeah, when I replace this load with RE load, okay. So, you know, we were saying that it this load will conduct the current I naught when H1 and H2 will be in forward conducting mode. Okay. Now, earlier the voltage was like same. This Vs. Okay. Vs is Vm sine omega t. Okay. And there will be some finite value of E. So the voltage across this H1, what it will observe, V across H1, it will observe Vm sine omega t minus E, right? If you apply KVL at this point, okay, in this entire, assume only H1 and H2 is conducting, okay? So H1 and H2. Huh, this is Vs, this is E, this is I naught, okay? So H1 will observe the voltage when this load is not conducting, and that is Vs minus E, okay? And we wrote Vs is equal to Vm sin omega t minus E. Now, when this E will be higher than Vm sin omega t, because E will have some magnitude, let us talk in numbers, okay? So let us assume it is 10, okay? And let us take Vs is equal to 50 sin omega t or 20 sin omega t, whatever. 20 sin omega t. Okay. Then 20 sin omega t will start from 0, right? Because it is sinusoidal property. Whatever the peak magnitude, it will start from 0. Okay. When this 20 sin omega t will become 10 at alpha is equal to 60 degree, right? Cos 60 is half. Yeah. So at 60 degree, or till 60 degree, this voltage across H1 was less than 0. It means it doesn't matter that your supply is positive or negative, right? It doesn't matter until and unless your supply value is higher than E. Then only this H1 can become forward bias. Okay. Before that instant, your switch will not be in forward biased and it will not conduct. So that is the influence of your battery on the supply. Okay. So I hope you got this point. And after this point, now you are free to provide the pulse wherever you want to provide, right? You you can even provide pulse before 60 also, but this switch will conduct only after this 60 degree. Okay. As soon as this switch will come in forward biased mode, then only it will start conducting. Or you can give pulse after 60 degree so that your pulse or that losses of your gate drivers will be lesser. So you can try to provide pulses after 60 degree. So that is the influence of E on the, or sorry, battery on your rectifier. So let me draw the waveform of it and let me also compute the output voltage. Okay. So this angle, what we computed when we equated 20 sine omega t is equal to 10. So this angle we can say something like phi. We can say phi. Okay. So this phi, why I am calling it phi? We want to generalize the term that when it will start conducting, because not every time the values will be like kind of a straightforward. Okay, sometimes your value of angles will be in point or decimals. So phi will be sine inverse E by Vm. Okay, so this angle phi till phi, this is the phi, this is the alpha. Okay. Huh. So now about output voltage. What will be the output voltage from 0 to 5? You would have got some idea about that. Could you let me know that value from,
E.
yeah, correct. Thanks. So from 0 to 5, V naught will follow the E. Okay. V naught is this voltage. And since no current is flowing, uh, at least before alpha, no current is flowing. So it will be E. Okay. And after that, if you trigger at alpha, it means till alpha it will not conduct. So from phi to alpha also it will be E only. Okay. And after that, it will follow your supply property and it will conduct till mm, till pi minus pi. Why so? Uh, yeah. Why I'm saying that it will conduct till pi minus phi, not till pi? Because the region is again the same, right? Your V naught or the voltage along your switch H1 that will again going lesser than E. After this point, your V naught will try to means I mean supply 20 sine omega t will be lesser than 20. So again, your H1 and H2 will be in reverse bias. No, sorry, in forward bias. Sorry, no, in reverse bias only, but it will not conduct, right? So till phi, it will follow the property of your supply, that is Vm sine omega t, and after phi, its magnitude will again become E, right? So I hope this waveform is not messy, but this is it. So if I want to compute the average value of this waveform, again we have waveform in front of us, so we can easily compute. So 1 by pi, since it will repeat after every pi, again from pi plus alpha, it will again follow this thing. Okay. So from 0 to 5, or here till alpha, 0 to alpha, the value of Vs or V naught is E into d omega t plus alpha to pi minus phi. Here from alpha to pi minus phi. Do not confuse it with pi minus alpha, okay? Because alpha, once you triggered the switch, it will conduct till your pi. In at least in that zone, it will be biased towards pi. But after here phi is in picture, so it will conduct till only pi minus phi. So Vm sine omega t d omega t, again from pi minus phi to pi, it will be E into d omega t. So this is the expression you can derive from the waveform. And quickly, if I try to write it, E into 2 alpha, right? Sorry, E into alpha plus uh, plus Vm cos alpha minus cos pi minus phi, okay? And again E into pi minus phi. So it is just left till simplification. So E into alpha plus phi, okay, 1 by pi plus Vm cos alpha cos pi minus theta is again minus cos theta, so plus cos phi. So this is your overall expression. If you try to mug it, it will be really difficult because alpha will be variable and there are so many expressions. you just try to draw the waveform based on the condition, and you can easily write the expression. It is just one or two step thing here, right? So any doubt in this RE load? In next session, we will discuss RLE load, and after that, we will discuss single phase semi converter, and then we can move ahead with three phase. So any doubt in this?
No, sir.
Okay, then fine. Thank you. We will wind up now. Yeah, thank you. Yeah, no, you may ask. Hello. Yeah, no, do you have any doubt?